Very good. And screen share. That's today. We'll do this.
Okay, so this week was fun. I got to process data from the drone flight we conducted on Sunday. Which was cool. So this was me. I feel like these photos kind of tell me I have to get a haircut, but yeah, we conducted the flight around 7:10 a.m. The temperature was 21 degrees and there was some light snow. It was really cold actually.
Very cold.
Ground temperature was read at 1 degree, but the thing was really inaccurate. I think at one point it read 145, right?
Yeah.
Yeah.
Yeah, we were done.
Um,
That was weird. So this was like the thermometer that I use in my kitchen, like often like totally accurate. So it must have been something about like when the sensor gets cold,
yeah.
it starts giving off really weird numbers.
Okay. So like it only works in like room temperature environments. Or
Yeah.
something.
Yeah, I've never had to do anything like that before, so that was weird, but yeah.
So we did system pre-checks. I was able to take the drone off, do landing stuff, fly it forward and backwards, which was cool. That drone was nice and easy to fly. So yeah. And so for the data collection, that we used the Mavic 3T and it got thermal and RGB. And then yeah, and so we did 2 flights. So GeoPilot 1 had 1168 thermal and 1168 RGB, 85% side lab, 90% front lab, speed 7.5, 120 AGL. Expected ground sampling distance was 15.82. So drone pilot 2 was 1550 thermal images and 1550 RGB, 30% side lab and then 90% front lab. And the speed was a little bit slower at 4.8 and then 50 meters AGL for a little bit lower, so you get higher spatial resolution. And the expected ground sampling was 6.5. Yeah. And so in processing the data, especially with the thermals, I utilized the GitHub thermal converter a lot. And what was interesting about the thermal converter is that they had like different ways of converting it, where you could like maintain RTK data, which I thought would be useful in terms of reconstruction, but it actually wasn't as useful as I thought it would have been.
Oh, how so?
The results just didn't show up, didn't like they weren't better or worse really, you know.
Okay, yeah, let's talk about that during our meeting. I'm interested. Last week, I found something that said, somebody said that the RTK doesn't get embedded in the thermal images anyway, which may be true. So if you really found no differences, we should look and take a look.
Yeah.
I believe you. In fact, I was just having a conversation with Carl about that. He's trying to run his big data set for Rapa Nui, and he's got like, I don't know, 30,000 images or something crazy. And when you run PPK, which is like RTK, but post-processing instead of real-time kinematic, it's post-processing kinematic. It wipes out the orientation of the camera from the metadata that's embedded in each image. So anyway, long story short, there's not always that much different. And the reconstruction is the same, whether using RTK or not. Like it should reconstruct exactly the same. What will be different is that the positions of everything will be more accurate. So
yeah. Okay. Yeah. What was also interesting is that it allows you to put like I'm not really familiar on this either. Is that it allows you to put like emissivity, distance, humidity values in. And I just did like the defaults that it has up there.
Yeah. Hey, that's great. Okay. So we'll talk about those at some point, but one of the things that catches my eye right away is distance.
Okay.
It's set to 5, which That ain't right.
I
So,
don't- like, I-
no. That's great. I used the defaults too, and I was getting weird values, and I wasn't paying attention to what those. Usually the defaults are generally pretty reasonable.
Yeah.
That's absolutely not reasonable.
Okay.
So we'll have to fix that, because I was getting temperature values that were off by, like, the relative differences seemed okay, but like the absolute values were
Yeah,
like, it was like 10 degrees Celsius off or something like that. That was great.
yeah.
Great.
So with that, like you can see like on the top, like I separated the files out into like RTK thermals,
Yeah, that's
thermal
good.
disk and all that, and then put the emissivity. So yeah.
Very good.
Yeah, so I tried playing around with multiple conversion types to see if it would get a better reconstruction. And so this is for Deer Pilot 1 of just the RGB. That one came out really good, but it took a really long time to process. It actually took like about 12 hours to
Did you do it
process.
here?
Yeah,
Cool.
and so.
Hey, you got a little piece of the parking lot.
Yeah, the parking lot came out really nice. And there's also like a little piece of like the water well.
Looks really
Is
good.
the black is on the ground or is the gaps it didn't capture?
Where?
It's like still many black in the middle.
I think, yeah,
That's the water.
That one
there
Kind of
was
a
a,
marshy.
all mushy thing.
So water often doesn't reconstruct. It's the reflectances change, and it just doesn't. Water almost never comes out, so that's normal. You got some fragments at the top of the right-hand one.
yeah.
So we'll talk about that during our meeting, but that's caused by images that get aligned but incorrectly. So it makes these little fragments. The reconstruction there is actually not too bad. You could go in and manually clean those out, and I'll show you how to do that in Cloud Compare. But we can I'll show you how to do to fix it in
Yeah,
structure in Pix4D.
Yeah.
Cool, very good. But you used to do the video captures, those look good.
I used a snipping tool.
Perfect. Oh, and it can do video?
Yeah.
What?
Yeah.
Oh,
Cool.
I love these meetings.
Yeah, and these ones don't have like the triangle meshes in, 'cause, like when I put those in, it just like made it look really weird. So, yeah, I had to put those in. But yeah, anyways, these are the quality reports that I decided to put with these. So 95% for the Deer Pilot 1 and then 75% for Deer Pilot 2. And yeah, I guess what surprised me the most was like I guess I just didn't expect it to take 12 hours, but you know, I went home. So
Sure, yeah. That's not so unusual. I think one of the reasons why it takes so long is these images are pretty high resolution, so I think these are probably 20 megapixel images. So that's big, and then it's 1,000 images, so. Yep.
Alright, so these are the ortho reconstructions, which, yeah, Deer Pilot 1 didn't come out, like, it kind of surprised me. I thought it would come out way worse, but it was a roughly, I think, 50% images were calibrated. Deer Pilot 2 obviously didn't construct nearly as well because of the less overlap,
Right,
lower overlap, but yeah.
Yeah. cool.
Yeah, these two have the triangle meshes in it because I just thought it made it a little bit better. So yeah, this one had 53% and then the other one had 32.
Okay,
And then I actually did it again because like I was just playing around with it yesterday and then it actually gave me 65. So
oh, what did you change to?
I don't think I changed anything. I think it was the same data.
Yes. My processing also has these problems. It's like first time is 50% and another time is down to I think 70%.
Yeah, that can happen. Yeah, you got 67% difference between the initial and optimized internal camera parameters, and it's got a red triangle. Anytime you see a number that big, we should figure out what happened. It could be that the internal model is just not, like the initial model wasn't very good. Sometimes that happens. It could be that like a bad reconstruction will often show that because it's trying to reconstruct the external environment, but it's also trying to reconstruct its internal, like the physics of the camera itself. And so almost all the time, if you've got a bad external model, you've got something going on the internal model as well.
Okay, and then I decided to take note of like a few thermal images, because this was from Deer Pilot 1, so like 1132, there's like a tiny red dot here. And it actually shows up in Deer Pilot 2 as well, which is interesting. The photo 257, I just wanted to like see if that was water or not, and yeah, it's water. So, and then 935 actually has two dots, two really red dots in that one location. And I like looking through them at first, I don't think we captured any deer, but 935 there might be a possibility.
Cool, let's take a close look. Yeah, I didn't see any either when I looked at it.
Yeah.
But I wanted to talk, there's one really bright spot, which is I think what you were looking at in 257 maybe. And I thought maybe that one was, but then I thought it was water. Yeah, the water showed up very warm,
Yeah.
which was neat.
Oh.
So like
Relatively warm, not very warm.
so Deer Pilot 2,
Oh,
like it's like you can like obviously since it was closer more to the ground, you could see.
Yeah, this is.
And I don't know
Yeah.
if those are rocks or if they're sleeping animals, but could be something.
yeah, that pattern looks a lot more like
Yeah.
animals. Cool. Cool. You think they're deer?
They could be. It was hard to tell when I was like zooming in on the photo, but we can look at it again.
Cool.
Yeah.
Nice work.
Yeah, the one for 1132, I think it was just like, I think there was just like a patch of ice that was melting. So I'm not sure exactly what it is, but it was interesting that they showed up in both drone flights. I thought maybe, I thought maybe they would be moving around.
That would be, what kind of ground would that be? I mean, it's pretty close to the water. Do you think it's like kind of wet and marshy?
Yeah, could be.
It seems like deer wouldn't want to sleep.
Oh, this one? Yeah.
Yeah, but I
Um,
don't know. But maybe that's not what that ground is there. It just looks the same as that one.
yeah.
These two are the same place.
Is it the same
No.
place? No.
I don't know.
Because what is it like? They were roughly the same number too. So this was 1132 on Drone Pilot 2 as well, and then the other one was like 940.
Huh.
So
Huh. Well, it might not be deer, but it might be something else.
yeah,
I wonder how big they are. We could make a measurement and see how big they are. Maybe they're pretty small. There's that object in the lower left there, which I'm trying to like, it's hard to get a sense of scale. You know, like I don't really,
yeah. Plus, I assume I took a smaller screenshot of.
yeah, let's take a measurement and we'll see. Neat.
So you asked me to try to figure out this deer duplicates problem. I gave it my best shot.
All right.
So, in this photo, in this kind of scenario, there's 9 deer. That's true to the total. However, because of image overlap, there's double counting. So in this scenario, you actually double count, like you're double counting 2 deer in one section, so that gives you 4, and so that'll give you like, and then there's 2 overlaps. So then you quadruple count, 1 deer 4 times, so then you get a total of 16. That's how I interpreted it. And so for me, when I was doing it, the number of double counts increases with the overlaps by a factor of 1. And so to find the true count, I said like you would do the total detected number of deer minus the number of overlaps times the deer detected. So like where N1 and N2 is the number of overlaps. And then, so in this case, you would do 16 minus 1 overlap, where 2 deer are detected, minus the second overlap where 2 deer are detected, and then where there's 4 deer being counted, there's 3 overlaps. So then you do 3 times the 1 deer that is being detected. Which, yeah, I still like working out this problem a little bit because like, it definitely is useful for like computer, like the automated detection, because like computers well, it's easy for the human eye to like understand that that's just one deer, but can a computer understand without like this from now to them.
Right.
So, yeah.
Cool, all right. A good first run at the problem is a good start.
Yeah.
There. Awesome.
So, yeah, goals, improve data processing. We talked about overlaying RGB onto the thermal data to try to create a better reconstruction.
Mhm.
I would like to find a way to like color the orthomosaics because the way the pictures showed up are really cool with like the orange and blues.
Mhm.
That was really cool. And then new data collection at some point would be cool, and then finalize master's committee, finalize thesis proposal, and then just work on course schedule, because yeah, I want to take the advanced remote semester two.
Awesome. Good work. Again, oops, let's do this. All right, thanks. Okay. All right, a couple of little things here. Oh, I forgot to put my goals slide on. You forgot to say what your goals were. Wait, did you say what your goals were?
Mhm.
I forgot. All right, good work. I didn't. All right. So I'll try to remember what my goals from last week were. Well, one of the reasons why I didn't get as much done this week as I would like to was I was finalizing the report that I had to do for the Solomon's Island drone LiDAR project. So that's done. So I was really happy to get that done and a day early, which was great. All right, so this was a fun one. I'm really into 3D prints. You can see I've got my puzzle on the floor. It sounds like they're going to print one of those out and put it somewhere else on campus. I gave one to Rick Shoemaker, who gave us the AR sandbox. He really liked it. In fact, he sent me an email. So we may see that model around on campus, which I'm going to redo it. So I might tell him to wait. But anyway, one of the things that I want to do is print one of these giant 2-meter versions. But you have to join these panels together. So the maximum size on a print bed is, depends on your printer, but mine is 260 millimeters. So I usually print these out as 250 millimeter tiles, a nice 1/4 meter chunk. But then you have to join them together. A couple of years ago, for the one that's hanging up at Virginia Tech, I just took a soldering iron and I adjusted the. I had like a dimmer switch that you could plug it into, so you could like just manually kind of adjust the amount of energy that was going in, and then so just. But this new soldering iron has a precise temperature control, so I could just set the temperature of the head to the melting temperature of the filament, and then just like I should have got a close up, but then just like basically like weld / solder the two pieces together. So it ended up really good. I'll bring it in this time. I couldn't bring it in, but I'll bring it in. And it worked really well, and it seems like a good solid join. And it was much easier than the last time I tried this. I'm on a project with Matt Bandy, and he's working on some of the archaeology, like World War II battlefield mapping stuff, but in his regular job, he flies drones with cameras to do things like wildlife surveys. And in the Southwest United States, so tortoises are kind of one of the things that he's after. So before we flew, I know this is a couple days before we flew on the weekend. I just wanted to hit him up and be like, what should we be shooting for ground sampling distance? And his advice was he tries to get 30 pixels in the long dimension to reliably identify something in the RGB image. So for a 1.5 meter long deer, just as a ballpark, that broke down to like a 5 centimeter ground sampling distance, which even our 50-meter flight was a little bit short of that. I think we would have had to fly at like 35 meters or something, which we could do. But it was really helpful to get somebody to sort of say what, and I'm going to hit him up too at some point about the overlap problem, because I think this is something that he does. He doesn't like make a 3D reconstruction. He just like flies. So he probably has a formula like this, but I want to have us take a crack at it first and make sure we understand the problem, and then we can ask him. But he thought that because we're using thermal imagery, it would probably be easier because it should, you know, I don't know how hot a deer looks like on a camera, but you know, way hotter than the exterior environment. So that's different than like you're looking for a brown tortoise on the brown ground. So that would be harder. So I think we'll have to see how it works out. I think there's a good chance that what you spotted were animals, because it would be an unusual water pattern to have like two separate pieces. Oh hey, how's it going? Guest visitor Adam.
Well, yeah, during meetings.
Yeah, that's right.
Leave it over here. I'll put them in there for you.
All right, thanks. See ya.
See ya.
When we were, so we ended up flying from this parking lot, which is called M1, which was a really great launch spot. Like we could see it very clearly. I think that's definitely the spot to do whatever we want to do in here. You know, being on the ground, we could see it. But I thought, how do we sort of quickly assess what we're going to be able to see from a certain place? And I think a couple of times ago, my approach was to use like Q ground control, plan the mission, set the height, export the KML, load it up into Google Earth, and then define a camera at your position. And then you can literally just sort of like look around and like see the flight path of whatever it is. On Guam, it was not reliable. So even though on like everything was in there just so, and it looked like we were going to be able to see everything from our launch site, we could not. And we had to have an observer down below to see it at certain points. So I wanted to look at other ways to make this assessment. So Google Earth at some point added in a viewshed tool into Google Earth, which is really handy. And so the idea was to define your launch point as the correct XY point, but then set it up off the ground at whatever your flight altitude is. So it's sort of like a reverse problem, right? It's like, what can you see from this spot versus what could you see from here? I'm not sure that that's a one-to-one relationship, but I think it's probably pretty close. But it didn't work the other way, and that was exactly the correct problem. So I don't know. This seems like a pretty good ballpark. I mean, looking at what we're seeing, so this is the result of that. So from where we launched 120 meters up, this is what we should be able to see. I don't think it's quite right here, because I think we could see it in this area as well. There's sort of a ridge line that runs basically here. There is sort of like a little mini ridge here, but I think we could see all of this. In fact, we lost track of the drone as it was flying, but it was within our line of sight. We just like couldn't see where it was. And we verified that on the second one. But I think this looks about right. I don't know. What are your thoughts, Peter? Like ballpark, what we could see?
Yeah.
And Chad, does it say you've been in the preserve a good deal?
I think probably if the signal can reach that out.
It can, yeah, the signal is good.
It's good.
Yeah.
It should be good.
So it wouldn't cover, this is the Campus in the Woods section.
Yeah.
So what's the guy's name that we've been talking to? Dylan, yeah, he had said that this was maybe a spot where deer might be located. But he also said like it was the spot where we flew, and like maybe one of these spots down here was also pretty. So I mean, there's plenty of deer territory over here to survey even if we don't get this. This was tough because it's right by a road and there wasn't really a good launch place where we felt like we could see it the whole time.
Yeah,
This is just a screenshot of sort of setting so you just set the altitude and then set it to relative to ground and then, yeah, I think that this is a plausible guess.
Pretty good, yeah.
So this is based on like where the ridge lines are. I think this is sort of the maximum extent of the polygon that we could cover. But we'll talk about this at the meeting, maybe Peter, and sort of see what we want to do for round
Yeah,
two.
That's a big area.
I think we should probably try to get as many deer flights as we can. Ideal conditions or no, until the leaves come on, and just see how it goes, right?
Yeah.
nice.
Now that we can maybe do one more flight together, and then I think probably you could do them on your own.
Okay, cool.
And then the last thing that I wanted to note, this was kind of cool. When we were out there, we could see what the drone was seeing. And I noticed that there's all these like downed trees.
Yes.
And I was like, oh, that looks like tornado damage based on some of the other stuff that we had done in years past. And so I looked it up, and indeed, there was a giant tornado that was a part of a tornado outbreak on May 31st, 1998. There was like a dozen or something tornadoes that went through this part of the country. And there was one that basically went right by Binghamton. It was like a 60-mile long track. I don't know, the data is in here. Length is 60, I think that's 62 miles or 62 kilometers. This was where we were doing our drone survey. And then this is a highly coarse track, right? So they were just like here, here, here. So I think in reality that the tornado actually did go through this spot. And I talked to Erin Otter, who teaches some of our physical geography classes, and I was like, do you know about this tornado? And she's like, oh, I definitely do. This was part of this outbreak and it was whatever. So I'm going to chat with her about it. I don't have any project in mind with it, but it does dovetail with two projects that we've done before on tornado damage. The idea was, can you add value to what we know about a tornado by looking at the damage the tree damage in a forest, right? Can you estimate its strength better? Can you estimate its track better? Clearly track better, like you can, you can do that. But based on how many stems are down within a certain, does that give you a good measure of its strength at that point, right? Usually the way they measure damage is how much damage did it do to this building, but it doesn't hit that many buildings, but it hits a lot of trees. So if you could use the trees to help you get a better guess about its strength, maybe you learn something interesting.
Interesting.
All right, so this is the big one for Addison mostly, but it's important for everybody. So this is why I wanted to talk about it at a lab meeting. You never know when the stuff that you're going to do is going to kind of bear on things, and as we're going to see, this is the temporal problem mirrors the spatial problem almost exactly. So what we're going to talk about with time is basically just think of it as a spatial problem, and it's the same thing. So the question is, if I want to run a correlation on two things, on two things in time, how do I do that? And so an example of this might be like a stock price. So what's the correlation between Apple's stock price and McDonald's stock price, right? These are two things in time. How do I do that? The actual problem that we're trying to solve, is this one. So this is a plot from Addison. This is the occupancy versus collision. So occupancy, just who's in the space and moving around from the percept data, is the blue line, and how often people are interacting based on Addison's algorithm on the red line. So similar problem, right? A and B. There's a particular part of Addison's problem that's a little bit different. So while they both are in time, Addison's is on hours of day. So it goes from midnight all the way to the next midnight, right? So it's a cyclical time problem. So the basic idea of this is that just like for a spatial problem, imagine you've got a map, right, of like phenomenon A and phenomenon B, right? Land cover and I don't know, income, right? And like, is land cover related to income in some way, right? So you would run a correlation, you would want to run a correlation between those two in some way. How would you do it? And one thing to keep in mind is that space and time are both autocorrelated. The value now is very related to the value just before it and just after it, right? Like the stock price at this point is very similar to the stock price 1 minute ago and 1 minute in the future. And that's true in space, right? The temperature at this point is very related to the temperature at this point and that point. But the farther away you go in space and time, the less related they are. And there are ways to capture that relationship. So spatial statistics deals with that explicitly, but this is sort of a more basic question. So one way that people do this stuff is they might do a time shift and then run the correlation. So just because two things don't overlap precisely doesn't mean that like they don't, they're not related, right? If I put the bread in the oven, it's related to when the bread comes out of the oven, it's just a half hour later. You know what I mean? So there might be a time lag effect between phenomenon A and phenomenon B. So you might need to shift those to make them line up. So that's a lag effect. That's one way to do it. I want to kind of move back from some of that stuff because there's a lot of other stuff going on here. But one question is, how do we correctly describe the relationship between variable A and variable B that are taken like this? I mean, Addison's problem exactly is why we're looking at this. So we could run a straight correlation, but remember that a correlation or regression analysis assumes that all the observations are independent. Probably remember that from like A is totally different than B, right? Right, random sample, stuff like that. When we do this in geography, we would run like a spatial regression. So geographically weighted regression is one way that we would accommodate this. So that's sort of setting up the problem. That's nothing Addison hasn't seen, but this is starting to get kind of new, I hope. So when we want to run a regression, let's say we wanted to run a regression on these two things. So we've plotted these as two separate line plots, and the axes are different, right? There's an axis for occupancy and there's an axis for collision, and that's what helps them kind of line up in time. And we can sort of see the relationship between them. We can see that there's a relationship as one goes up, the other one goes up, but we're looking at it in time. But one way to process this would be to sort of like consider, point 0 times 0, and consider this the x coordinate and consider this the y coordinate. In other words, make it a scatter plot. So that's what's going on down here. This is a scatter plot of that data. Occupancy is on the x-axis, collisions is on the y-axis. And then I've labeled them with hours of the day so you can get a sense of, this is 1 a.m., there's midnight, there's 3 a.m., there's 9 p.m., and so on. So time is sort of mildly retained here as a label, but it doesn't actually figure in. So you could run a regression on this scatter plot, or a correlation, right? And I have pinned the intersection to 0, right? 0 people is 0 collisions. I want to sort of stipulate that in the model. And so when you do that, this is the relationship, and then this is the R-squared value. So clearly related, right? We can see this in both plots. We can see it in the time series plot, and we can see it in the scatter plot. Occupancy is definitely related to collisions, and the R-squared value is 0.96. And then our correlation is literally just the square root of that, right? So they're 100% mathematically related. But one of the things I always encourage people to do is to look at residuals, right? So residual is, if you use the model to predict the value, what's the difference between that predicted value and the actual value? So you can go back and calculate that out. So for instance, 1 a.m. is above the line. 10 AM is below the line, and you can see that here as well, right? Collisions are above the line here, and collisions are below the line there. So the residuals are basically taking you the same thing. So this is the residuals plot. Again, this is stuff that Addison has already done, just visualized now just a little bit differently. So here you can see the over prediction. In fact, I did it so that it's predicted value minus the, actual value minus predicted value, so that they all sort of line up the way that you'd expect. So this is more collisions than you would expect at this time of day, and then fewer collisions than you would expect at this time of day, and then more collisions than you would expect. And that's exactly what's going on here. It's just like a slightly different way of visualizing it.
Oh, yeah, those are residuals right there. Yeah.
Yep.
Yeah.
So what I want to do, so the residuals are a good way to sort of get at the non-randomness of the time component. Now, the non-randomness of the time component is actually part of what's interesting to Addison, right? Like to say that there are more here and there are fewer here, or vice versa, I guess. Like that's the interesting part. So like the lesson here is don't run ordinary least squares, because it's really valuable, right? Like these residuals are telling you an interesting thing about how these go. But if you factor out the time component, so another way to think of this is time alone predicts collisions, right? Even if I didn't know what the occupancy was, I could start making pretty good guesses about collisions, because there's a daily cycle to them, right? There's going to be more collisions in the middle of the day than there are at 5 in the morning. So the fact that I know that means there's information in there, and I can factor that information into the model to make a better prediction and control for that to get a better sense of what the actual relationship is between occupancy and collision. So at this point, I want to check in with Addison, because this is, as much as this is for everyone, this is specifically for Addison also. So Addison, so far so good?
Yeah, this helps clarify that a lot. I thought the stock thing was like super helpful in terms of an explanation for that, of just like seeing, of course, McDonald's and Apple don't really have that much to do with one another. There's like this underlying kind of feature that explains both of those. And so I guess this is the same way that the time is kind of like occupancy isn't the only thing determining collisions. Time determines occupancy, and time determines collisions.
That's right. Yep. Cool. And this was great, because this is the kind of thing that I'll fold into my next spatial analysis class. I've got a bit on like temporal stuff, but I kind of gloss over it because I've never really had to do it. And so I'll fold a lot of this stuff into that the next time I teach the class. So I'm excited to do that. All right. So how do we get, so if time of day is related to collisions, how do we get that into the model? So one of the things that you don't want to do is just add, so in multiple regression, we can have more than one predictor variable, but we wouldn't want to just use hour of the day as our predictor. And the reason for that is, even though broadly speaking, you can imagine sort of a line that goes here, we know that this is a cyclical data set, right? So it goes from 11 p.m. back to midnight. So if you just use the linear numbers here, you lose that cyclical nature. So you could totally misfit the data. In this case, I think it would probably work okay, but it's really a bad idea. So what people usually do is they transform the scale from 0 to 1. So midnight 0 is still 0, but 11:59 becomes 11:59 or 59 seconds or whatever becomes 1, right? The instant before midnight becomes 1. Does that make sense? So you're scaling time, 0 to 1. So instead of going 0 to 23, it goes 0 to 1.
I see.
That part makes sense. And then you just transform these with sine and cosine.
Oh.
Now the neat thing is, this is exactly what a clock does, right? So when you do that, you get this circular pattern of data. The x coordinate becomes the on a 24-hour day, right? So a clock face does that with 12, right? So you just repeat the cycle twice. But if you do it for a 24-hour day, then imagine this is like a 24-hour clock. which exist, right? I should have grabbed a picture of one. Like you can make a clock with 24 numbers instead of, right? So so anyway, does the clock analogy make sense to everybody?
Mhm.
All right, so these are a couple of references, mostly for Addison here, about doing this. And this comes up in space because azimuth is exactly the same, right? If you've got a directional component to your data that you're working with, that goes 0 to 360 degrees, you need to process that in exactly the same way. You do a sine and a cosine transform, and you get two values for each of them. It becomes like an easting component and a northing component. And in fact, the tornado damage bit is related. One of the previous students had to break, had a direction component of the tornado and wanted to include that in a regression model. So you apply the sine and cosine. Simple math, but it's a neat idea. So this is how that works in practice. So T represents the hour of the day, 0 to 23. So the hour of the day is as sine is just the sine of that, effectively, 2 times pi times that. The cosine, the same thing. And then when you build your regression model, so you've got again, we're trying to predict collisions. So this is occupancy, and then the time component, sine time component, and cosine time component. Does that makes sense? So it just becomes a multiple regression problem, but now we've got 3 predictors. 2 of them are time. So far, so good. So when you do this, you get a 0.991 correlation, or R squared value. So the time is adding value to the prediction. And how do you know that? You look at the p-values for the individual predictors. So X, which is occupancy, super significant. Always remember that this is rounded. So this is like the way that you report this is p is less than 0.001. There's some fraction of a number here. P is number 0. The cosine component is 0. So that is also significant.
Yeah.
The sine component is not by itself significant. And we can talk about, I'm going to do a transformation here next that I think explains this a little bit better. But the time broadly is significant. Okay, so one thing that you can do is you can change the direction of your clock face. So right now, midnight is at 0 and noon is down at the bottom, right? According to this transformation. But we can align our clock so that the top of the clock is the peak time. And in this case, our peak time happens, you could just ballpark this at like 4 p.m., right?
Yeah.
So somewhere in there. You could change it to 3 p.m. I think this one is 3 p.m. I think this one is 5 p.m. So I just was like 4 p.m. is a ballpark number. It doesn't really matter. So to do that, all you have to do is subtract whatever your peak time is, and then do the same transformation. But now, I gotta make this go away. I hate that thing. Now, the cosine is the peakiness, right? So instead of midnight at the top, peak time is at the top, and off peak time is at the bottom. And after the peak is on the right, and before the peak is at the left. Does that make sense?
Yes.
All right, so the cool thing about that is now you can interpret the coefficients of the regression. So occupancy is still significant, of course. The cosine is not significant, right? So 0.22, which means peak hour doesn't really modify our understanding of how those two things are related. But before peak and after peak does. And I'm going to jump back here, and that's what you see here. Before the peak, occupancy exceeds collisions, but after the peak, collisions exceed occupancy. And that's what's being captured in the sign before peak, after peak. Does that sort of make sense?
Yeah.
Now I'll mention, so far there's nothing that I've done here that isn't obvious in this plot, right? Like, this plot did all the work. We can see the relationship between the two, we can diagnose, the one is higher than the other at this time or whatever. What this does is it supplies the statistical and this relationship is significant, right? Like, that's what the regression does. Does that make sense also, Addison?
Mhm.
Kind of a annoying but important part of a scientific paper is to like have the stats in there that say this is why we can believe these results. Otherwise, if you sort of tell a story about plots, this sort of adds it. Okay, so the last thing, how am I doing on time? Ooh, it's late for you, Peter, sorry.
Yeah, no, but that was interesting.
There's a little bit here on space, but it'll be recorded. I'll send you a link or whatever, so.
Okay.
Very good. All right, see you,
Thanks.
Peter. Okay, so so far, interestingly enough, we still haven't taken into account autocorrelation.
Oh,
We've included time, right? But only in the sense of time predicts collisions, right? We know that there's going to be more collisions later in the day than in the early morning hours. So we've added that factor in there, which means that we've dialed in to some extent what the real relationship is for our coefficient. And in fact, I think we'd want to use the t-score here to get a value that basically tells us how significant the collision. Anyway, our refined understanding should be better. Like, this should be more representative of exactly how much occupancy affects collisions. Okay, but so we factor in the time thing, but we haven't factored in the autocorrelation bit. And so I was like, well, I sort of understand this in space. So I went back to, I looked up the Esri documentation on geographically weighted regression, which is okay. They've got a couple of pretty good posts about that. But I ended up finding the original paper by Brunson and Fotheringham and Charlton, where they introduced geographically weighted regression in 1996. Sometimes those original papers were really good, especially, I think scientific papers now are kind of clunky, but a lot of the stuff from like the 60s to the 90s is much more readable than the stuff now. So anyway, I read it, and they basically give this example that said, because I was like, what is GWR really doing? Okay, it's taking into account spatial autocorrelation, but exactly how? And the way that I think I can explain it is this. It basically functions like an interaction term in a regression. So an interaction term helps to refine the relationship where things can actually reverse if two variables go together. So I'm going to try to. The example that I give in spatial analysis is climate change skepticism is associated with education. So the more educated you are, broadly speaking, the less skeptical the more you believe in climate change. And it's related to political persuasion. So the more Democrat leaning you are, the more likely you are to believe in climate changing. But there's an interaction effect where the most educated, most Republican people are less likely. It sort of modifies that relationship in kind of an interesting way. So the pattern actually reverses. So that's what an interaction term can do in a regression. And that's what I would say happens spatially with geographically weighted regression. And the example that they give in the paper has to do with car ownership. And the idea here is that, broadly speaking, unemployment is associated with not owning a car. And this is from a while ago. But the idea is, if you lose your job, you can't afford your car, you don't have a car, right? So the more unemployment, the fewer cars. That's broadly true, but it's particularly more true in some places than others. In a city, it may not be as strong of a connection because mass transit sort of washes out the effect. But rurally, it's more true because you kind of have to have a car. So I think I kind of butchered that example a little bit. But the idea is that the relationship might be true in more places, in some places rather than others, right? And city urban is an easy way to think about that. And so by taking that into account, you kind of know when or where to apply the rule of this relationship. And the gist of it then is you're sort of fitting these regressions locally, right? So like, what's the relationship between unemployment and car ownership here? What's the relationship between unemployment and car
yeah.
ownership there?
Yeah,
And so you define this neighborhood, blah, blah, blah. So imagine if, so that would play out in this case, Addison, if occupancy was associated with collisions, but not always, right? Like, let's say that there was a consistent pattern at some point, but then at some point it just became random, right? Like maybe from 2 to 6 a.m. It's not that it's a positive relationship, it's not that it's a negative relationship, it's just random. I don't think that's true, but like that's the example. Anyway, I couldn't figure out exactly how to make this happen temporally, but what I could do is say, well, we've already spatialized this problem. Can we just use the tools we have to solve it? So if we imagine that our sine and cosine values are coordinates, which they are, right? Again, think about this clock face, like we're literally spatializing time. Then we can run a GWR on it because we've just now spatialized the time component and we'll just use the two variables. So all we have to do is say, how does occupancy predict collisions? And the way that I defined this was to set the number of neighbors to 10. So the idea is like you'd run a regression on these 10, and then those 10, and then these 10. So you're running a regression effectively for at each point for its 10 closest neighbors. Does that make sense, Abson?
Mm-hmm.
Right. I don't think that this works. It worked. First of all, I guess I'll say the guidance in the Esri documentation says that you should do this on hundreds of observations. It doesn't work very well in small data sets. So I don't think it directly applies to this. So I don't think this is going to wind up in your thesis, probably, Addison. Although what you could do potentially is instead of summing all of the values, you could run this on the original data, right? So each hour of the day for the whole semester. So, 24 times however many days there were. So you could probably do that and then transform the coordinates. I'm not sure that the numbers would, we'll talk about whether we think this is worthwhile or not. But anyway, the R squared value is 0.93, which is not that helpful. That sort of gets at basically the same correlation that you get if you just run the correlation, right? I don't remember what that was, but
It was really close to that.
so not much value added. 0.965, and this was 0.93. So, I think that there just aren't enough observations here. I thought it was interesting though, as a way to spatialize time and then try to solve the problem that way. Sometimes you got to reach for the tools that you've got. So I had fun working on this, Addison. It was more intricate than I had imagined. I thought there was going to be sort of a Stack Overflow post that was like, here's how you do it, there you go. And that was not the case. So and I've been wanting to look at this for years.
Yeah, thank you so much for doing that. Because I looked at stuff that I could not find anything, and I just did not know where to go with it. But this explanation made a ton of sense too. And so I guess with the geographically weighted regression, it's only using X as an explanatory variable because the time is being represented as space.
Yep. Yeah. Okay. I tried putting those in there, and I ran a bunch of these. So I guess I don't remember exactly what happened. But yeah, that was the idea. Are already being included as a space factor, which I think is correct. I think if you added it back into the regression also, it'd be like adding latitude and longitude into your regression, which you wouldn't ordinarily. I tried when I first sent you the stuff on Slack. I had the number of neighbors set to 2, which I think is too small. that gave a very high correlation. But then you're running a regression on 3 points, basically, which I think doesn't make any sense. So I don't know what the right number is here. You can have it make a guess for what it thinks the right number is. But it's not really the right answer anyway here, but it's super fun. I was really excited when I realized we could just run a GWR on it.
I really like the residual plots too.
The residuals I think was really helpful. That's maybe the plot that I would suggest throwing in the thesis.
Yeah, either the residual or the one that had the like, I guess what would be the trend line, and then the hours of the day like on each side of the trend line, depending on like the number of collisions.
Yeah, cool.
Yeah, thank you so much for doing this.
Why don't we throw it to Addison next, because let's form sort of a continuous thought.
Let me. I didn't put anything specifically related to the time stuff in there because
Well, that's all right.
I knew you were going to cover it, and so I was like, I'll let you do this, and I'll understand it for the time being, and then maybe next week, depending on what I end up doing with it, then we can go in mine. But yeah, I have a quick presentation for this week. So the main thing that I was focusing on was like the algorithm. We decided to change from, I guess, using the term ground truthing to validation, because ground truthing kind of makes the assumption that like we actually know what is happening on the ground. And so I'm not doing that. I'm looking at the animations and trying to then use my best judgment to say, do I think this was a real collision or not? And so there is no objective answer necessarily to what counts as a collision and what doesn't. And so the term validation ends up fitting a lot better. I spent a lot of time on Tuesday evening fixing the code to build the animation from the overlaid frames. I still don't know why it was not working. But I think what was happening is that it was trying to resize each image while it was building the animation. And so it wasn't saying that there was a memory problem, but I think that's what was happening, because it failed at like the 734th frame every single time. And so it started out super fast, and then it started getting slower and slower and slower. And then eventually it hit frame 734 of 3600 and it would fail. And so I was working on this for like hours upon hours, trying to figure out how to fix this. And randomly, I ended up setting the like scale of the image, and I didn't know that that's what was happening. But I ended up setting the scale of the image and like specifying it while building the animation in FFmpeg, and so that ended up fixing it. And so good news there. So now I'm able to actually do that. And so oops, just 2 slides are the exact same. Yes. So I wanted to take like a couple different kind of like levels of busyness in terms of like hours to do this on. And so the one that I did this week was this like extremely busy hour. And so I actually like went through minute by minute on the thing and just like wrote down what I thought, because I was having to like pause and rewind and like rewatch some of them and everything. And so to like try to remember, okay, here's another one, here's another one. So I broke it down from like the first minute to the second, second to third, did it that way. And so I kind of decided and kind of found that like the busier the space is, it's a lot more difficult to determine like whether or not something is a collision. Which I think that makes sense, because you have so many people that are just like, this person was just talking with this person. Next thing you know, this one guy stops talking with the other person and talks to a different person right here. Yep. And so it's like they're having like these little micro interactions that are just kind of like associated with these events. And it's really hard, especially when the density is really high, to say, oh yeah, that's a collision versus no, it's not. And I also think the algorithm probably struggles with that a little bit more than when it would. And like, it's picking out those low density environment collisions super easily because the signature is so strong and obvious, where you have two people coming from a very long way apart, they're walking towards each other, they stop, it's as obvious as it can get. Whereas like in these high density environments, their movement patterns are going to be a little bit less like obvious in terms of like a consistent data signature. And so when I was doing the validation for this, I ended up making 3 categories, which was yes, unsure, and no. And so for the unsure, I would say I could also kind of define that as like probably yes. But it's just like it's hard to tell for sure whether or not it was like a real collision or if they were talking with someone or if they were talking for a longer time. And then there were some that were no's, which were like if 2 people were talking for a very long time, every once in a while it would get like those 2 people's interaction would get double counted. And so like something like that would be a no, where it's like that should be that those, percent probably generates a new ID for one of those 2 people, and then that gets messed up from there. But that's one of those that like I don't want those to be counted, even if they do get counted sometimes. But so I have the video of this. We don't have to watch the whole thing, obviously. Is it playing for you guys?
Yep.
Yep.
Okay. So like there's just like some examples of like when people end up having them. So that person and that person, that person and this person. And so like I'm having to, go back and not go back like that. But like go back and slow it down and say, look at this space again. And like sometimes the like very first interactions don't always get picked up, and it might be because the 2 people are too far away. Sometimes the signatures get picked up really quickly and easily. But there's ones like that where you have 2 people that are probably already talking to one another. And especially in that high density environment, it's not necessarily easy to tell even between like which of these 2 people it's saying a collision is occurring with. And so like it's like, yes, there's people here and they're talking and it's probably, matching that signature. But would you call that like that kind of like spontaneous collision sort of thing? And it's like it's kind of hard to do that. And that's why I kind of had that like unsure category. But do that. And so I broke this up into like the yes and the no's and unshores. And so for this hour, the like definite yeses were 56 of 82. So 68.3% of like a perfect yes, absolutely true positive. And then if I included the ones that I was like unsure about, that number spikes to 87% or 88%, which I think is pretty decent. Oops. And then there were, in terms of false positives, it was like, I guess that would be a little over 10%, like 11 or 12%, which is maybe a little higher than I would want it to be. But I also think that during that higher density environment, the just like the number of false positives is going to be higher. But yeah, that's what I got for that. And so I want to do a couple more. I have another hour picked out. And so probably this weekend, but maybe early next week. I'm gonna do probably 3 more like hours worth of data and try to find a couple more that have that like medium sort of density. Just to get like a good balance between like, denoting, and even if like the values here aren't like as perfectly like statistically sound because they're kind of like these arbitrary yeses, arbitrary maybes, and arbitrary nos. It's at least then giving me the insight for discussion results and things like that to say, the algorithm performed, or I felt like the algorithm performed better in these lower density environments, whereas like during these high density situations, even with like some filters in the algorithm to like try to reduce and like limit those false positives, they still do happen.
Yeah.
Yeah, I think it was a good start for that.
False negatives?
Or
Do you have a sense of those? Like things you're missing?
I was trying to track them in the high density. It's pretty much impossible.
That's fine. Yeah, I agree.
And so like I wrote down when I saw an obvious one, but there were so many that could have been like, should that be a false negative? I don't know. Yeah. And so I ended up getting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 false negatives that like I thought the algorithm should have picked up, but it didn't.
10, in a single hour, 10, what was the,
Yeah, 10 in that single hour when there were 82 real collisions. I think it missed 10.
okay, is that different than the no that you've got here?
Yes.
That's different, okay,
Yeah. This no, I guess would be the
false positive.
false positives.
Okay.
And then
10
the
more
false
false
negatives or something else.
Okay,
But it's hard for me to watch for the false negatives and
no, that's
on that one, too.
fine, I don't like, that's a totally reasonable number. So I'm happy if you can report something like that. Just, you know, again, I think any kind of because somebody's gonna wonder, right, like, it forms an incomplete picture if we don't know what we're missing, like, is this 10% of the collisions that occurred, or is this 90% of the collisions that occurred, right? Those are very different things, and what you're saying is like, we think we're getting
Most of them, at
most
least.
of them. And that's a good thing to know, right? Like that adds a lot of assurance. I mean, your animations add a ton of assurance. Like, I think when you show that at your defense, and then, you know, if you present this at a conference or something like that, that's going to help convince people like that this thing works, right? Because it's not like you got a bunch of dots going on here. Like, pretty much when people come together, you can see it with your eyes. You're like, yep, that's an interaction. Yep, that's an interaction. So all of this together, I think, is making for a very strong argument that it works. And like, I'm really excited that it works this well. Like, I didn't think that it was going to work this well.
Yeah,
Yeah.
me too.
Works really, really well, which is fantastic.
Yeah, I was thinking the true positive rate was going to be somewhere around like 30%, 40%.
I would have been happy with that. That would have been a great first draft. But this is far exceeds that. So good work.
Yeah, I'm excited. And so I had a couple other notes and I can't figure out. Oh, here they are. So I guess I kind of like during this, and especially during the high density environment, I kind of like paused at times when like I saw something that kind of created this like data issue. And so there were kind of two specific ones. I should have put these in my slides, and I just forgot until now. The kind of two specific ones that kind of sparked in my mind. The first one was those like really long discussions. And specifically if two people come together in a space over here where my right hand is, they start talking, they talk for a long time, they then walk together, and then they stop, and then they kind of keep talking in a different spot in the space. That got double counted a couple times. And so like those were kind of those false positives where it was like it is like it was the same two people. And so it was just like, I think it happened 2 or 3 times to where it was getting recorded as another collision. But it was the same discussion that happened for so long that Percept eventually gave one of those two people a new unique ID. And so like that's one that is probably close to unavoidable without going back to Percept and like trying to tune some of those settings so that happens even less.
Yeah.
So like that one is what it is. And then the other one was there was one in this data set. I don't remember where it was. I could almost I would pull up the timestamp if I remembered it. Somewhere in the 6th, let me see, where there was like a reflection collision. And so the good thing is that it wasn't someone colliding with their own reflection. It was if the glass is here, person A and person B have a collision here, and their reflections have a collision with each other, which I thought was really interesting. And so let's see, this would be 0 to 1, 2, somewhere from 5 to 6. And it happens with like right there. And so the timing was perfect. Wow. Okay. Let me really slow this down. So where like, so now we're almost watching it. It's a little bit faster than like its natural speed. But I think what happens is it's one of these people with one of these people. And so they come in and they pause. but it's not actually, or I guess it's maybe these two people, but it's not actually it's not that this person is having a collision with their own reflection. It's that this person is having a collision with this person, and this person's reflection is having a collision with the other person's reflection. Which I just thought was interesting. Those are ones that like I can really easily trim those out of like the final data sets just by using the mask and saying, you know, if any collisions happen outside of this area, just get rid of them. But I thought that was really interesting that it's not the one way that I was kind of expecting it to be.
Yeah, yeah.
Um,
I guess people don't get that close to the glass. There's like,
yeah,
so maybe that helps separate them out beyond the meter and a half or whatever. It's really neat.
yeah. And if there is a situation where someone does get that close to the glass, those might end up happening. I would guess that those numbers are probably super small because I didn't see any during this hour, which is good. Means that it's not like a super big issue or anything.
Oh, I've got a question for you. So we're recording these. I guess the percept data is twice per second.
It would be, let me think. For the collision algorithm, it's just taking the first response of the thing per second. So it should be that the percept data is like designed to match up with each frame of this. So like the dot would just follow.
Your collision algorithm basically runs at 1 hertz. Is that fair to say?
Yes.
Okay. What would happen operationally and detection wise if you had 30 frames per second? Would it work better? Would it work the same? What would happen to your computation time?
The computation time would probably go up exponentially just because of a few of the ways like the code was written. Now, I guess I fixed those. The computation time would definitely go up a ton. I would think the data signature might get a little bit better. Just because like there's a chance that there's like some interactions where there's actually one right at the beginning where this was one that I said was like initially a false negative between this person and this person here, I think. Where they probably did get closer than that like 1.5 meters, but with the percent points being only once per second, maybe their points never got closer than that 1.5 meters because it was like a really short sort of interaction. And then it waits till later to where I think they come back and start talking to one another once more. Maybe they don't. But like one like that looked like one, but it ended up getting missed. And I think it was just like that could be a result of percept really only being once per second in that frame.
I think in general, our data would be a little bit better if the frame rate were a little faster. I feel like 1 second is a little slow to capture all of the behavior that we would like. I know that we would need 30, but five frames per second would probably be nice. I don't know, just something to think about. Sort of how could you?
Yeah, I will make it 0%. I just wrote that down just to remember that because I could probably add that to like my future work or like limitations section. So bulk of my work for this week was in my thesis stuff. So I responded to I said probably not all of them, but most of them. But I really got to keep chugging along. There's really only a couple of weeks left until the document needs to really be kind of polished up. I think my results section is kind of starting to get there. And I think the discussion section might actually be a little easier than the results section because the discussion section you can kind of just like it's easier to talk about the implications of the results and kind of tie that into like some of the other literature and stuff than I think it is to like talk about the results itself. But I think I'm feeling pretty good about it. And then the last thing that I have is job news. I accepted a remote position with Timmons Group, which is an engineering firm based in Richmond. This was the company that I was actually, I think I talked about it last week during the lab report. And after the lab meeting, they were really looking for someone. They were hiring a couple more people for like their geospatial team. And so I think they were really more so looking for someone that would be in person. And I was in the process of kind of telling them like I don't think it's gonna be able to make it work just with the relocation and stuff. And then they ended up calling me back and were like, hey, we're willing to try this, letting you work remotely. So I'm excited for that.
Cool, congratulations.
Congratulations.
Thank you. I'm excited.
And Richmond is close enough that you could like, go once in a while.
Yeah, and that's what I said too, and I think that was helpful probably because like I mean I really don't mind going in once or twice a month. It's just the full relocation is tough because I live with my partner and she has a job here and likes her job here, and so it's like it's hard to be like, and now you have to find a new job.
Yep.
So,
Cool,
that
well,
makes
that's
that a lot
awesome
easier.
news.
But yeah, so then I got some fun job interview memes down there. But that's what I have for this week. My goals for next week are really work on writing a lot. And then also OGs next week. And I should probably start working for that because I did sign up, and so I'm excited for it. I just need to do it.
Yeah, well, fortunately, this would be everybody's third OJUS, is that right?
My
I think it'll
third
just be my
OGS.
second.
Second? Oh, okay. Well, it should be a little easier than the last time, I'm sure.
Yeah.
All right, thanks, Addison.
Yeah, of course.
Uh, can you see my screen? I have a pretty short one this week. So update from last week, I've been able to make all the models finish up, and I validated all the results, and I've got the scores for everything. So going from like listing these, deep learning is performing the best, and I think Percept is the second. And OpenCV, like both of the methods are like not the best, but like I think it's pretty good regarding the precision and like for the background abstraction specifically. So yeah, these are the values. I think I'm pretty happy with like all the methods. I wished I had spent more time on the frame differencing one, but this is like not giving me the best of results. So these are the basic.
Yeah,
Go
one
ahead.
little piece of advice, align your numbers so that they align right in the
Okay.
table. Makes it easier to make visual comparisons between numbers.
Okay.
Give me a second to absorb this. These are the final scores, huh?
Yes.
Right, cool.
I think except deep learning, every other method is like does not have the best recall. So more false negatives.
So let's see, best F1 score, deep learning for sure.
Yeah.
All about the same, DSM a little bit better. Precision, it's a bit more of a toss up. Background subtraction does pretty well. That's the winner. That's the best.
Yes, it is the winner. Yep.
Oh, that's interesting. That's
Yeah.
a good
So
finding.
whatever it detects is like very good at like detection, but like whatever it misses, that's where it like faulted.
Okay, that's cool. And then recall, deep learning again, pretty strong.
That is pretty good.
And still very good precision score. So it's not like it's
Yeah.
a bunch of false positives in there. And Percept is doing okay on recall, but not so good on precision. A lot of false positives, which partly you said was due to people on furniture, and partly due to double counting.
Yes. multiple signatures of the same object. Yeah.
And you could imagine double counting, you could probably, if a point is within X distance of
Mhm.
another point, like, and heading is the same, combine them, so maybe some
Yeah.
post processing could boost those numbers a little bit.
Yes. For Percept, that could definitely work. Yeah.
All right. Is this what you would have expected? How does this?
I think like at the end, background subtraction performed better than I had expected with the time I spent on it. I think OpenCV is like the most flexible among all these because like with deep learning, with Percept, you are stuck to whatever you have. But like with background subtraction, I performed 6 different iteration of parameters, and I think if I spend more time, I could, I don't know, maybe like make this much better, knowing that it's detecting like it's not detecting a lot of stuff with like a low value of recall. So yeah,
Cool.
so these are the traditional metrics. Like these are like pretty much understood. The other metrics I'm going to show is like the chamfer ratio and the BDR. So each second has a distinct value for chamfer ratio and BDR, and I have like aggregated these. So these are the values right now. I'm just going to explain what values I was expecting. So the closer it is to 0, the more similar the set of points are for chamfer ratio. And it performs pretty good for everything. I'm surprised the background subtraction has a value of like 0.000, which is like the ideal value you'd expect. So yeah, for this, I think all the methods are like performing pretty well with background subtraction standing out. This basically says the coordinates it is detecting is perfectly aligned, and I was expecting a low value for Percept because of the time synchronization. That's one, and I think this is the highest value. So that's as expected.
Okay.
Yeah. And for the BDR, it's basically looking at the spatial alignment of the points, and Percept performs pretty good. The deep learning models perform pretty good. I think for the R square, even the OpenCV methods have a good value. So I have a separate slide like talking about how I got these. So I just put these as like notes for myself. So sum up all the true positives, false positives, and false negative, and recalculate the aggregate precision and recall. I've talked about this in the previous lab meetings. And similarly, like for the F1, I aggregated all the values using this formula. So that's pretty much known. And the other ones that I want to talk about are like taking the chamfer ratio, like aggregating it. So the chamfer ratio could range from 0 to like 2 or like even more. Uh, and the thing to note here is 0.5 is the same as 2. And if I average the like those values directly, it does not make sense. But if I take the logarithm of it, 0.5 and 2 kind of become the same. So I decided to take the logarithm and then average the logarithmic value. So this kind of takes into account for like 0.5 and 2 being the same thing. So that's how I aggregated that. And for the R square, Dr. Pringle mentioned that you could not like directly average R square values. It does not make sense to. So there is something called the Fisher transformation that basically converts the R square, the R value to a Z value, and you could average the Z value or the Z scores. So there's a Fisher transformation that I applied. On doing that, one thing I observed was all of the final aggregate R square came as 1. And that was because it's performing a tan inverse, and tan inverse, anything divided by 0 is a 1. So what I did was I ended up changing all the frames that had a perfect R square value, 1 as 0.999. And upon doing that, I got these kind of values. Otherwise, all of these are coming out as one, not being separable from the other. So yeah, these are just like basic notes on how I converted these, and finally average all of these scores, perform an inverse Fisher transformation, and then square the final value. That's how I do it.
These are great notes. Trying to make
Yeah.
sure that all of this gets folded into the method section.
It is in there.
Question about the BDR for Percept. That value is a lot higher than I would expect.
Yes.
What's causing that?
I'm not exactly sure. I think the way we are doing the BDR square is like we are using the Hungarian algorithm, and we are discarding everything that does not fall within the closest distance. Is that true, Dr. Bengal? because like we decided that we'd do the bootstrap where like if a set had like a lot of points and a set had small points, but like I look at the build score function and it does not use the bootstrap. It just takes the closest point.
Huh. So it's not getting penalized for its false positive rate, is sort of making up for
Yeah.
it, right? Yeah,
I
okay.
think that's what's going on. Yeah.
What happened to the
like
bootstrap?
I think I looked at the notes on the thesis and you had commented about like these iterations were performed, but I think we decided to skip the bootstrap like and then just go with the Hungarian algorithm because the build score function only does not have anything with the bootstrap.
Okay, I'll try to remember to
Yeah.
take a look at that. In light of that, I mean, does BDR work then? I mean, that seemed like
Yeah.
I still don't mind that it's in the thesis. I'm less convinced
Yeah.
all the time it's going to make the manuscript, but I guess it should be in the thesis because it's a learning, it's something we learned.
Yeah.
We did. Let me check the bootstrap thing, and I'll try to do that today, and just see what's going on with that.
Good. So there's a separate function called BDR bootstrap, but I didn't see it being called in the big function that I've been using. Yeah.
Okay.
Yes. So the other thing I've been working on is like trying to find out the aggregate movement overall. Like, how does each method define aggregate movement in the space? So what I did was I took all the three methods first deep learning, and I used the model that had the best accuracy results. That is the DSM, and I'm trying to get detections for like the whole month of September. And like this is me running it on a single day. And I was surprised that it takes almost 3 hours to do it for a single day
Yeah. Woo.
because it has like 86,000 frames. And that was something I didn't like think about. I'm like practically running it on like 86,000 times 30 frames.
Huh.
And we also thought about doing it for a whole semester. That might actually take a month to do.
Yeah. Well, yeah. Clearly, we made the right call there. All right, 3 hours. Let's. I mean, if you don't start having memory errors and slowing down, that's 8 days per day. So you'll take 5 days. No, 4 days.
4 days.
You're gonna let it.
And I,
It's not so bad. The weekend,
yeah,
like
yeah.
as long as it works
I
and
think,
doesn't crash, like that's all right.
and I think I wanted to like even talk about this in the discussion section. Deep learning is very data intensive as well, and it's like taking a lot of time to like run aggregate movement parameters.
Yeah, it's fast enough to handle it in real time. It's
Yeah.
just
Like a month of data in 4 days. That's pretty fast too, right? Like a month of data set being post processed within 4 days.
it's not too bad. And maybe there's some hacks we could do at some point. We're not that we're gonna, but like, all right. So are you gonna proceed with this? Like,
Yes, I think I
Okay.
am. Yeah, I just need to
what's
figure
what
out
about
like
OpenCV? How long is that gonna take?
sorry. For OpenCV, it's better. I've got it in the next slide. So for OpenCV, it took like 2 hours, but I was running these parallelly. So I don't know if it's a good idea to run these both at the same time. I think I'm just going to do the OpenCV first because it's performing faster, and I'm going to switch to deep learning next.
Yeah, actually, that's probably true for deep learning. Come to think of it, I mean, I would just let it go, but I bet there's a way to parallelize the deep learning, so that you're tackling, because it's just applying it by frames, right? So you could literally just
Yeah.
throw all the frames just in different processes. But
Yeah.
no, this is fine as long as it's going to be
Yeah.
done. It's going to be done on Monday or Tuesday. Like that's good.
So the OpenCV is gonna finish, and while this is running, I want to like find a better way to do the deep learning because I'm doing it like day per day. So yeah, that's what I'm trying to figure out. Yeah, I'll probably be able to get all the results by like mid next week. So I was like pretty okay with that. So the OpenCV, I'm expecting it to finish by the weekend, and yeah, I'll probably have stuff to show. The other thing that saved my time like was trying to Addison. Thank you so much. I got the percept data. I was able to filter it for the month of September, I cropped it inside the study area. So I think I'm pretty happy with doing it for only September. It's very data intensive. So the idea was to see how much occupancy or movement is occurring inside the space with like each method. So I was able to do it thanks to Addison for this. And so I just ran a small like kernel density map, and this is what I have. So yeah, of all the kernel density maps I've ever run, I think this speaks a lot. So I was like looking at it and like trying to understand what it is doing. I was expecting, like when Dr. Pringle asked me, what are you expecting from each method? I was saying Percept will give hotspots for furnitures. So this is furnitures, these are furnitures. This is Kevin's office, is like, I think near the closet and everything. So I was expecting a lot of people sitting in the CID space, but like I think this is what caught my eye, like people just walking in to like walk out again.
Yeah, and the stairs.
Yeah,
Yeah,
the
this is
stairs
great.
and the elevator. So I was like fascinated with this map. Like I don't know if I can make it better or like do something else that like even make these stuff stand out. But I think I'm pretty happy with the first kernel density I ran. Yeah. So that's one thing I'm working on parallelly. I think I'm going to get like the same stuff for the OpenCV. One other thing I was working on was like Dr. Pringle asked me if there's a spatial distribution to false positives. So my idea was to just get the annotation data set, run a 2 meter buffer on it, and then just see if like I can detect the points that do not fall under it. But that failed epically because I didn't realize I had to do it on a frame by frame basis, but I managed to do it because like I had to compare each second with each second of detection. But I was able to do it, so it's not that bad. So when I filtered everything that did not fall under it, so these are the results of the deep learning. The deep learning made me feel optimistic about what I was trying to do because I'm kind of getting like where I'm getting the like false positives. I think this is like the community table that is present. Some of these are like near the furniture, and that's kind of what I was expecting. Some of those are like near the elevator. So near the elevator, it's pretty difficult to identify if it's a person walking because the coverage is not the best, and it's like sometimes it's very strong signature, sometimes it's like not as strong. So this I was pretty happy with. I think I identified what are causing the false positives for deep learning. What did not what I did not find very optimistic was for the so I let me check real quick. So this is for the deep learning results. So I identified all the false positives, and I'm not seeing anything with the false positive results. I tried to compare it with the uh, deep learning model, and I think the most false positives are like this, and but I don't know what to make sense of this.
This is, wait, which one am I looking at now?
This is Percept.
This is Percept, okay.
Yes,
Well, the pattern is different.
it is different. Yeah,
That's okay. I mean, that's basically as far as I want to get, is sort of like an overall comparison. There's a lot more false positives. I think the question is like, do they happen in one particular place? And like, probably not. I mean, mostly that looks like it correlates pretty well with like activity, like that's where people are moving. That's all right. I don't think you have enough data. I mean, one thought was maybe you'd want to normalize this to occupancy, but I don't think you have enough data to make that a good plot. I think you're better off just sort of like, using your intuition and experience to do that rather than some actual overlay. Looks good.
yeah. It is detecting more points than usual. I didn't find anything for Percept, and for OpenCV, the same thing kind of occurs again.
Yeah.
So like you can see
Yeah,
deep
they're all
learning
a
and
little different.
OpenCV
Yeah.
Sorry?
They're all a
have a
little
similar
different.
pattern. Yeah. I think the one thing I wanted to mention was, so if you see these points,
Yeah.
so when I look at all of these three density maps, what I realized was OpenCV and deep learning have a similar pattern of false positives, but Percept does not.
Okay.
So these are the points from deep learning, and you can see that in the next slide. In this slide, like the points and the hot like red zones are similar. That's like something that's not consistent with the precept. So yeah, so that's
It's
where I
maybe
got
great.
with the
3-panel,
Yeah.
A, B, and C. In fact, I was gonna ask, and I'm hesitant to ask because I know you've got a lot on your plate already. How hard would it be to do this for false negatives? Now that you've got the script, is it just a matter of like changing this one column to another column, or
I just need to identify the logic behind false negatives. So yeah, because like with false positives, I was just saying if something is within 2 meter distance of annotation. But for false negatives, I just need to find the logic. I think if I think it's right, I should be able to do it in like 1 hour.
okay? I guess I don't really understand mechanically how you're keeping track of this stuff because you've got when you run your stuff, you're already counting whether it's a false positive or a false negative, right?
Yeah.
Well, beyond my ability to discern at this point, like it the best. So as long as you're on top of it, like that's fine. I think it would make a neat 6-panel like diagnostic plot, right? Like false positive, false negative, deep learning, OpenCV, Percept, and then you can compare all of them. I don't see anything in here that raises any alarm bells. I mean,
Yeah.
on this one, for instance, you can see OpenCV is missing some people by that door, the northeast door. That's interesting. And we've seen, well, I guess these are false positives. I've seen false negatives around there, right, where it's not
Yeah, it's not detecting.
coverage. Yeah, I think that this will be useful for false negatives, and this is great.
Yeah, I think I just need to think it through. If I like write it out, I think I should be able to do it. Shouldn't take too much time. And I'm just like learning it.
Anything outside of the polygon that you're showing here, that's the mask. So anything
Yeah.
outside the polygon would have been discounted anyway.
Yeah.
Okay.
So that's where I got. So I'll probably run it for false negatives again. I want to see how that works as well. I was pretty happy with like doing this. So yeah. So goal for next week, finalize OpenCV model that's done. I'm just going to process data for aggregate movement and I'm adding the false negative in the goal. So the major goal is to write everything, polish like the results of discussion section. I made good progress in the discussion section, but I think I need to like decide what I want to put inside the result section. For now, I have a lot of names, but I was wondering if I should also like put links of videos of each algorithm working. Yeah. So that's it for this week.
Yeah, awesome. Cool. All right. Any last items before we break? I'm probably going to be in the documents this afternoon. I've got relatively few meetings today, so I'll try to do some editing this afternoon, and I guess probably not tonight, but tomorrow.
Yeah.
Very good.
Don't forget, I might be AFK until tomorrow 5-ish, but I'll be back by Saturday 5.
Oh, yeah, no problem.
Yeah.
Very good. All right, take it easy.
Yeah.